Good morning, chemistry students. Here are your ChemQuest 22 ionization trends corrections. Separating charges. Examine figure 1 below, where there are 3 pairs of metal spheres that have different amounts of charge on them. The spheres in diagram C are closer than the others because they have the strongest attraction. Figure 1, attraction between metal spheres, diagram A plus 3 minus 3, diagram B plus 4 minus 4, diagram C plus 7 minus 7. And again, they just told us that strongest attraction. Okay. So they're closer together. Question number 1. Which would be harder to separate, the 2 spheres in diagram A or the 2 spheres in diagram B? Why? Well, again, which one would be harder to separate? Diagram B would be because there's a stronger attraction, which makes them harder to separate, plus they are closer together, which makes them harder to separate. So the spheres in diagram B would be harder to separate because the force of attraction is greater because, or we can say maybe due to the higher charge difference. +4 and -4, and also the spheres are closer together. Which makes them harder to separate. Just like magnets that are close together. So again, kind of 2 reasons. Number 1, right, the greater force of attraction because of the higher charge difference, and then closer together, which also makes them harder to separate. Question 2. Draw 4 diagrams of the following atoms: lithium, nitrogen, and fluorine. So lithium, when you look at your periodic table, is atomic number 3. So it has 3 protons, 2 electrons in the first energy level, 1 electron in the second. Okay. Next we have nitrogen, which has atomic number 7, so +7. So 2 electrons in the first, leaves 5 electrons in the second energy level. That's nitrogen. Lastly, we want to see fluorine, which has 9 protons, which means it has 9 electrons, 2 in the first energy level, and that leaves 7 for the second. So this is fluorine. Number 3, for each of the atoms in question 2, compare the attraction between the nucleus and the outer level of electrons. So again, remember we've done this before, right? The attraction for this first electron would be +3 because there's no shielding. The second electron, it would be +1 because I have shielding of 2 electrons in the first energy level. When I get to nitrogen, again, that first electrons in the first energy level are going to feel +7 because there's no shielding. In the second energy level, they're going to feel a +5 because there's the shielding of the 2 electrons in the first energy level. For fluorine, in the first energy level, the electrons are going to feel that +9 attraction from the nucleus. In the second energy level, they're going to feel a +7 because of that shielding of the 2 electrons in the first energy level. So the second energy level is reduced by 2 because of the shielding of the 2 electrons in the first energy level. Second energy level, we can say kind of pull from the nucleus. So which atom has the strongest attraction between the nucleus and outer electrons? Right, so the strongest pull from the nucleus for the outer electrons would be fluorine. And again, that's because we have a +7 pull from the nucleus to those outer shell electrons. Number 4. Which would be more difficult if you wanted to remove an outer electron from an atom of fluorine or from an atom of nitrogen? So, because of the same reason we talked about here, right? Harder to separate magnets when there's a greater force of attraction, okay? Because that also makes the spheres closer together. So, what that means when we talk about nitrogen here and phosphorus is fluorine. Fluorine is a smaller atom because +7 to, because of the +7 pull. By comparison, right, nitrogen is going to be a larger atom because its pull is only a +5 pull. Okay? So the question here is, would it be more difficult if you wanted to remove an electron from an atom of fluorine or from an atom of nitrogen? It's going to be more difficult to remove an electron from fluorine because the atom is smaller, is one reason, and the pull from the nucleus for that electron is greater. Okay, so this means that it would take more energy to pull the electron off of fluorine. So for similar reasons as question 1, it would take more energy to remove an outer electron from an atom of fluorine than from nitrogen. The outer electron from fluorine feels a stronger force of attraction from the nucleus. So the next question is, would it be easier to remove an electron from lithium or nitrogen? Okay, so again, lithium is the largest atom because, right, it only has a +3 pull. And because it only has a +3 pull compared to, +1 pull compared to the +7 pull from nitrogen for that highest occupied energy level electrons, it would be easier to pull an electron from lithium. So lithium, because the atom is larger, and the pull from the nucleus is smaller. So it would be easier to remove an outer electron from lithium because lithium's outer electron experiences a weaker force of attraction from the nucleus. So information about ionization energy. The amount of energy that it takes to completely remove an electron from an atom is called ionization energy. The first ionization energy is the energy required to move one electron from an atom's outer energy level. The second ionization energy is the energy needed to remove a second electron from the energy level. The second ionization energy is always higher than the first ionization energy. Because noble gases have 8 electrons in their outer energy level, they are very stable, and therefore it takes a very high amount of energy to remove an electron from a noble gas. So again, kind of some things that they're telling us or making sure. So first ionization energy, we remove one electron. In the second ionization energy, we're talking about removing a second electron from that atom. They also tell us that the second ionization energy is always higher, okay, than the first, which is always the lower of the two ionization energies. And then they also tell us that the noble gases which are group 18 or 8A, okay, have 8 electrons in their outer energy level, which makes them very stable, and it takes a large, very large amount of energy to remove an electron from them. So question number 6. Which would have a higher first ionization energy, phosphorus or aluminum? You may want to draw a Bohr diagram to help you determine the answer. So we're going to do Bohr diagrams. Aluminum has plus 13 protons, so we have 2 electrons in the first, 8 in the second, and then it's going to have 3 electrons in the third. So there's my aluminum. Okay, phosphorus plus 15, 2 electrons in the first, 8 in the second, 3, 4, 5, 6, 7, 8. Remember, it doesn't matter where you put them, which leaves 5 in my third. 2, 3, 4, 5. This is phosphorus. So the question is about first ionization energy, which is what we already talked about with lithium, nitrogen, and phosphorus. So we kind of want to do the same thing. We want to look at the pull for the electrons, right? In the first energy level, the pull in aluminum would be 13. There is no shielding. I get to the second energy level, the pull for an electron is a plus 11 because I have that shielding effect of the first energy level that has 2 electrons. When I get to the third energy level, now I have shielding from the first and the second. That's a total of 10 electrons. So my pull from my nucleus is a plus 1. When I talk about phosphorus, right, my pull for my first energy level is plus 15 because I have no shielding. In my second energy level, I have shielding of 2, so my pull for my nucleus is plus 13. When I get to my third energy level, again, I have shielding from the first and the second, totaling 10 electrons in total, and so my pull would be a plus 5. So now the question is, which one would have a higher first ionization? Remember, higher means it's harder to remove. Okay, so this kind of question is asking, which atom would it be harder to remove that outermost electron from? Aluminum, okay, and I don't know why I put +1, sorry. It should be +3, right, because I have a shielding effect of 10. Okay, sorry about that. So the question is, which one would be harder to remove? So which one is holding the electrons more tightly? So it would be harder to remove from phosphorus, okay, is harder to remove. And again, it's for those same two reasons, because number one, okay, the +5 pull makes phosphorus smaller than aluminum. And number two, that +5 pull means it's harder to remove an electron. Therefore, phosphorus has a higher first ionization energy. Again, the person who wrote this answered it this way, phosphorus, because it has a higher attraction between the nucleus and the outer electrons than aluminum. Question number 7. Phosphorus and aluminum are in the same row of the periodic table. Lithium, nitrogen, and fluorine are also in the same row. Using your answers to questions 3, 4, and 6, what do you notice about the ionization energy of elements proceeding from left to right across a row on the periodic table? Does the ionization energy increase or decrease as you go across the period? So, right, we just said that phosphorus's ionization energy was larger and that aluminum's was smaller. And that was because aluminum's pull was +3 and phosphorus's pull was +5. When we talked about lithium, nitrogen, and fluorine, lithium's first ionization energy was larger and lithium's was the smallest. So we can say was the largest of the three. And again, this had to do with the fact that there was a +7 pull here, there was a +5 pull here, and there was a +1 pull here. So the question being here, okay, does the ionization energy increase or decrease as you go across a period? So as we go from left to right across a period, right, the ionization energy increases. We see that with aluminum and phosphorus. We saw it with lithium, nitrogen, and fluorine. So as you move from left to right across a row or period, the ionization energy increases. Part B says, explain why you believe this trend exists. So again, what did we see happening here? We saw an increase in the pull of the nucleus for those outer electrons, which makes it harder to remove an electron, so the ionization energy increases. So the why, right, why this happens, okay, there is the same shielding, right, because the shielding doesn't change. But there's an increased pull of the nucleus for the outer electrons. Therefore, it requires more energy to remove an electron. Therefore, the ionization energy increases. Again, the person who wrote this said, this trend exists because as you move from left to right across a period, the attraction between the nucleus and outer level electrons also increases. For atoms with a stronger attraction for the outer electrons, it requires more ionization energy to remove the electron. Number 8, draw a Bohr diagram for sodium. So sodium has an atomic number 11. So it has 2 electrons in its first energy level, 8 in its second, and 1 in its third. So this is our sodium atom. Okay. Do you expect the first ionization energy to be high or low for sodium? So again, we're kind of looking at this pull, right? In our first energy level, it would be plus 11. There's no shielding. Our second energy level, the pull would be plus 9 because there's a shielding of 2. When I get to the third energy level, it's only a pull of plus 1. So do I expect that ionization energy to be high or low? I would expect it to be relatively low. Because the pull from the nucleus is only a plus 1. So again, the person who wrote this said sodium has a low first ionization energy because of the low attraction from the nucleus, the plus 1, for the electron in the third energy level. Question 9. The second ionization energy of all elements is higher than the first ionization energy, but in sodium the second ionization energy is extra large. Considering the structure of the sodium atom, explain why this might be. Hint, after 1 electron is removed, what is sodium's electron arrangement like? So, when we form a sodium ion that has a plus 1 charge, it still has 11 protons, but now it's lost one of its electrons, right? That's what it means when we talk about ionization energy. It means we're removing an electron. So now it has 10 electrons. So take a look at the periodic table. Who else on the periodic table has 10 electrons? Neon. And neon is a noble gas. And remember, back in our information section, we said the noble gases that have 8 electrons in their outer energy level are very stable, and it takes a very large amount of energy to remove an electron. So what's happened to sodium by becoming an ion with a plus 1 charge? It's begotten the electron configuration of neon, which we know is very stable. Okay, so its electron configuration is like neon, which is very stable. Therefore, it's going to take a very large amount of energy to remove a second electron. So remember, I've talked about it as the noble gases being the cool kids on the periodic table. Every element, when it forms these ions, these atoms that have a charge, it's doing so in an effort to become like a noble gas, to have the electron configuration of a noble gas. And sodium does that when it loses its first electron. So it doesn't want to lose a second electron. So it takes a very large amount of energy to remove that second electron. The person who wrote this said, after the first electron is removed, sodium has the same electron configuration as neon with 10 electrons. It is like a noble gas, and therefore to remove the next electron is very difficult. Number 10. A certain atom in the third period has a third ionization energy that is unusually high. Using the same reasoning you used for question 9, name this atom. So we're in the third period. So again, we're looking at, right? Third period means we're looking at these elements here. Okay? And the question says, again, a certain atom in the third period has a third ionization energy that is unusually high. So that means it loses one electron, it's still not a noble gas. But it loses a second electron, and now it's like a noble gas. So what element in this row of the periodic table, if it loses 2 electrons, does it become like a noble gas? Magnesium. Right? It loses 1 electron, it's like sodium. It loses its second electron, it is like neon. So magnesium, because it is in the third row or period of the periodic table, and it has 2 more electrons than neon, a noble gas. After the first 2 electrons are removed, the third one is extra hard to remove because it will need to be removed from a noble gas-like configuration. The other way that we can kind of think about that is we can draw magnesium's Bohr diagram, right? Magnesium is plus 12, 2 electrons, 8 here, 4, 5, 6, 7, 8, and 2 electrons in its outermost. So this is magnesium. So the question is, how many electrons does it need to lose to get to this second energy level being completely full? It needs to lose these 2. So first ionization energy fairly low, second ionization energy pretty low. Now it has the electron configuration of neon, and so its third ionization energy is very high. Information. Trend in ionization energy in groups. Consider the following figure of diagrams of 2 magnets that you wish to separate. Figure 2, separating magnets, diagram D, and diagram E. Notice the difference between them is the distance here. So the difference is the distance between the magnets. So question 11. Would it be easier to separate the magnets in diagram D or those in diagram E in figure 2? So which is going to be easier to separate? Okay, and it does tell us, assume that each magnet is attracted to the other and that the size of attraction is the same. Take only the distance between the magnets into consideration. So if these are equally strong magnets and we're trying to pull them apart, which one's going to be easier to pull apart, right? Hopefully you remember from playing with magnets when you were a little kid, that diagram E. Okay, so the magnets are easier to separate when they are further apart. So it will be easier to separate the magnets in diagram E. Number 12. How does the distance between the outer level of electrons and the nucleus in phosphorus compare to the distance between the outer level of electrons and the nucleus in nitrogen? So again, remember in nitrogen our pull here is +5, and in phosphorus we have a shielding of 10. We also have a pull +5. So notice that our pull for those outer electrons is the same. The question here is, how does the distance between the outer level of electrons and the nucleus compare? Right? Well, right, even just based on my pictures, which aren't necessarily drawn to scale, but certainly the distances between the nucleus and the outer electrons are different. Okay? And the distance, right, this distance is smaller, and this distance is larger. So the distance between the nucleus and the outer electrons. Number 13. Based on your answer to question 12, would it be easier to remove an electron from nitrogen or from phosphorus? Right? This is going back to this idea about magnets that are easier to separate. That's also going to be true when we're talking about forces of attraction. So we want to know which electron would be easier to pull off. An electron from the third energy level of phosphorus or an electron from the second energy level of nitrogen. Right? And it's going to be easier to remove an electron from phosphorus because it's the same attraction over a greater distance. Therefore, it's easier and requires less energy. So again, the person who wrote this said, okay, it would be easier to remove an electron from phosphorus than from nitrogen since the outer electron is farther away in the phosphorus atom. Number 14. Nitrogen and phosphorus are in the same column on the periodic table. From your answers to questions 12 and 13, what happens to the ionization energy as you move down a column in the periodic table? Right, so we're going down a column, and our ionization energy decreases because it's the same attraction for the nucleus acting over a larger distance. Therefore, it requires less energy. So as you move down a column of the periodic table, the ionization energy decreases because the size of the atom increases. So remember, our atom size is increasing because we're adding another level of electrons. So that is the end of the corrections for this ChemQuest. Have a good day. See you tomorrow.